All right, folks, we are doing this chapter 12 thing. All right, so first things first, this is a review of what you know from chapter 3, which you'll be needing and using in chapter 12. All right, so we're looking at how close students sit to the front of the classroom. So what row they're in, and does sitting closer cause higher achievement, or do better students simply choose to sit in the front? You can think about that. Hopefully you know what to do with this word. To investigate, AP Stats teacher randomly assigned, it's an experiment, students to seat locations in his classroom for a particular chapter and recorded the test score for each student. The explanatory variable in this experiment is what row the student was randomly assigned to. Do these data provide convincing evidence that sitting closer causes students to get higher grades? So, again, it was an experiment with random assignment. So that would be something we can do if that's what we see. Describe the association. So beginning in chapter 3, describe the scatter plot. You're looking for 3 words. I love this. This is okay. So you're looking for 3 words to describe this. Now, I think there's a weak, slightly negative, and then this isn't curving, so we're going to call this weak, negative, linear association, and then don't stop there. Name of the variable needs to go somewhere between row seat, I don't know what to call it, between seat location and test score. Okay. So the question was, does sitting closer cause higher grades? Looks like it's the opposite, right? No, those guys have higher scores. Close to, yes. People who are sitting closer have slightly higher scores than the people who are not sitting close. Using the computer app with this business, determine the equation of the least square regression line. So heads up, folks, in chapter 12, we're going to be visiting everything else here that we've been ignoring so far, but for right now, looking at these two. Specifically, this one is the name of the x variable. So this is the slope, which means this is your y-intercept. All right. So the equation is, now make sure you have context. There's 2 ways to do this. So step 1, if you want to do y hat equals negative 1.117 x plus 85.7, you can do that, but don't stop there. You want to say y hat is predicted test score. And x is row number. You can do that, or if that's not your jam or you think you might forget, predicted test score is equal to negative 1.17117 row number plus 85.7. So as you get further away from the teacher, your test score will start dropping. Calculate the value of the correlation. We have r squared here. It's currently written as 4.7%. We want to change it to be 0.047, and then we're going to take the square root of it. Now heads up, we said negative. This is r squared. It will always give you a positive, but you got to notice you're looking for a negative number right there. So you square root that business. Okay, gives me a negative 0.217 as my correlation. So we calculated that. That is weak. How do I know it's weak? It is less than 0.4, which is the cutoff. So above 0.4 is the medium, less than 0.4 is weak. Calculate and interpret the residual for the student who sat in row 1 and scored a 76. I think that's this person right here. So it looks like they're below the line. So we're going to say they're sitting in row 1. They got a 76. But we also need to know what, so to get the residual, your equation is y minus y hat. So we need to get the y hat, what was predicted for them. So we're going to go with negative 1.117, row number 1, plus 85.7. So the prediction for the student was an 84.6 as their test score. We got a 76. So their residual is a 76. What actually happened minus what was predicted. This is going to be negative. And we're supposed to interpret it. So this student got a score that was 8.6 points lower, that's my minus, than their row number predicted. Okay. Now, don't worry about it. This is a super weak relationship, so that line wasn't particularly helpful anyway. Next up, the slope. What does it mean to have a negative 1.117? So we're going to say for each extra row the student moves back in the classroom, in the away from the teacher direction, their test score is predicted to drop, that's the negative, by 1.17 points on average. Now, do I need all these wiggle words? Not really. This is a wiggle word, and this is a wiggle word. One is sufficient, but please make sure you have at least one. Otherwise, you're saying this will happen for every single person every single time, and that is definitely not what the scatter plot is telling us. Okay, now, interpret the standard deviation of the residuals. This is a tough one. This is an easy one to forget. So this one, this is your typical residual size. Why is it on average? Because the average residual is always 0. This is the standard deviation of the residuals, how far away they are on average from 0. So S is 10. Wish I could remember things. What did it say? 10.07. This is going to be the typical residual size or average error made by the line in predicting score from row is 10 points on the test. So on average, the line makes 10-point errors on predicting your test score. Is this a good or a bad thing? Generally speaking, we would like this one, the S, to be, S should be less than 10% of a typical Y value to be useful in helping you predict. So if we go look at your Y values, let's look at the typical Y value. It's my dog snoring, if you can hear that. So typical Y value is 80. This is 10. It's a little bit higher than 10%, but it's not horrendous. So I would say this is 10 out of 80, 12%. 12% error, which is okay. Right? It's close to the boundary of okay. It's okay-ish. Interpret the value of R squared. So this one's pretty hurt. This one is going to be kind of the thing that makes our line not useful. So changes in test score can, I'm going to say 4.7% of changes in test score can be attributed to, that's one of the ways to phrase this, accounted for, I'm just giving you lots of ways to phrase this, explained by changes in distance to the teacher. So row 1, you're close to the teacher. Row 7, you're far from the teacher. Is this a useful variable? In this case, probably not, right? This means we're missing 95.3% of the reason test scores change. Test scores are changing is unaccounted for. We don't know what it is. So we haven't found a very useful predictive variable. Not a great predictor. Explain why it was important to randomly assign the students to seats rather than letting each student choose his own. So if you have random assignment, that means that you are choosing, it's an experiment, No random assignment. That means you have some, I always forget this word, confounding variables, which means people choose where to sit. People choose where to sit near each other for similar reasons. So the row choice is not the same as other choices that are made together with the row choice. So other variables are entangled with the row choice versus researcher assigns row. So student doesn't choose row. What does this do for us? It means we control the confounding variables. And then hopefully equally distributed, about equally distributed amongst the rows. So we're saying this factor no longer matters. And then we can come up with something saying that we are now only looking at what effect rows have on our variable. So you're focusing on the effect that rows have on test scores. And we haven't found much of an effect. What other variables did the teacher control? What is the purpose of keeping these variables the same? So same teacher, same test, same instructional time, same chapter, and so on. Purpose is to reduce the variation in the response that is due to other factors besides seat locations. We're trying to isolate what effect does the seat location have on test scores. These kinds of things will include, so since we're controlling lots and lots of variables, this is helping us increase this, decrease the error, making it easier to see the association. We still don't see a very strong one. Does the negative slope provide convincing evidence that sitting closer causes? The causes part I'm not worried about. It's just how strong the association is, right? Is this association due to just random variation? It's very small, the association we're seeing, right? Ask students to describe what information is provided by the dot plot. How could we do this without a simulation? Okay, so this is kind of getting us into the new stuff in this chapter. So chi-square test for association is going to be two categorical variables. And just so we're clear, what we're doing in chapter 12 is two quantitative variables, right? So we are least square regression line business, two quantitative variables. So that's what we're doing. That's what we're trying to deal with. We don't have a tool for this yet. From all the other tests we don't have a hypothesis test that will allow us to compare two quantitative variables. So this is an important tool to have. So what all this is saying is if you look at the scatter plot, do you notice that maybe the scatter around the line is equal from row to row? If that's true, then we meet some of the conditions we're looking for the stuff that's coming.